report. Okay, for the lab report, I want to, for the abstract, I want you to include the finding or major data value. So this refers actually to numerical value. I think in your case, you did refer to a data table. You said that as shown in such and such table. And for that reason, if I'm correct, if I remember it right, I didn't take too many points off. But here, like for this experiment today, the IR values, they should show up in the abstract. Same thing for melting point, for percent yield. These are the numbers that they should show in the abstract, as well as the conclusion. So for the following experiment, please try to include those into the abstract and conclusion.
Will do. This document doesn't change, right? This, what you're showing me right now, this is...
No, that's part of the syllabus. That doesn't change, no.
Okay, I'll reread it again. Thank you, doctor.
Okay, and maybe the samples that I had, if it's from a document, that maybe the sample throw you off, but the sample, let me see. On the sample report, the tables were in the introduction section. The tables, the table for data, it should be in the in part of the result and discussion, not the introduction, unless the introduction, the table that contained there, it was comparing the boiling point, how close they are, and melting point, how significantly different they are. So that table could be in the introduction, but the finding, the major finding of the mass and the melting point, yeah, that one, it's, yes, that's okay. That part, it could go. That's not your major finding. That's given information from the experiment that could be actually part of the introduction, because it's coming from the introduction. Actually, my 1230 class, they were asking, where can we find information for introduction? I said, don't spend too much time finding information. Other places, your lab manual, when you read the experiment, anything that is before the procedure, you just summarize that, and that would be part of the introduction. So you don't have to actually do research for that. So that table was different. Yes, that table was data, given data that could be part of the introduction. I hope I answered your question, Natalia. Now, Charisse, your question?
Hi, Professor. Good afternoon.
Good afternoon.
I just wanted to make sure, this is for the lab for today, the Fisher experiment. I wanted to confirm that the mole ratio for this experiment, so when we do the percent yield, it's 1 to 1. Is that correct?
Yes, and I will go over, I will show you exactly the reaction that you're using to find the theoretical yield. Is the balance equation, and from the balance equation, it's a 1 to 1 ratio. Yes, very good.
All right, thanks.
You're welcome. Any other questions or concerns you might have? I didn't get to grade all the reports because they were not all submitted by last night, so I didn't grade anything today, but anything that was graded until last night I did. Christopher, I got your email. I didn't have the, okay, let me see what was, I think you sent me like 2 emails, right? Okay, what was the situation there? Was that part of was that picture part of the lab report already? Or you were sending me? Okay, you have the percent yield as part of the abstract. Is that what? Okay, abstract. But what about the melting point? Do you also have the melting point? Okay, I think I'm on the wrong page. Do you also have the, sorry. Let me read the emails. I did not put the theoretical yield, but I showed that. Okay. So theoretical yield is part of the abstract. Please also include the melting point. And for this experiment, the IR values, the peak area where your IR shows, and I will explain about that. Also, so IR values, melting point, percent yield, they all need to be included in the abstract and conclusion. So I might have said that you don't have, melting point and the theoretical unless I specified it. It would be something that I consider when I'm giving or taking points off. But when I write the comment, I write like general, that data missing or data value missing from the abstract. I am sure because I have to read the experiment. I may not read the few lines from his introduction or your data, because those are the numbers that I already did the experiment and I just go through quickly. But everything else, I have to read it. So I did get the theoretical yield, but there was no melting point. Please do not refer to the table, because the abstract is supposed to have the actual numerical value. And this is just one experiment, one report. The reason I tried to grade this before you submit the second experiment is to make sure that anything that it will cause like a point from your lab report, it will be corrected on the next one. I don't think I took points off for both melting point and for the percent yield, but I will double check and make sure that I don't take points off, extra points off.
Professor?
But the melting point was missing from the abstract, and the conclusion was not also including both the melting point and the and if it did, I'm glad that you sent the email so I can check it. I will check it again in case if I missed it, but I don't think I took points up for both of them. It was just one. But I will have to check your sure, I saw the abstract already, the screenshot for the abstract, and I will check also for your conclusion, definitely. No problem. Okay, any other questions that you might have before we start experiment 13? No questions? Okay. Experiment 13. Michael, can you tell me what reaction is involved in today's experiment? What is the reaction for the experiment? And I'm going to stop sharing the syllabus. I will share the lab manual with you. Michael, are you here? Yes, okay. Can you tell me the type of the reaction? What reaction is involved in the experiment, or what is the reaction for today's experiment? You answered already, most likely. Okay. Multi-step synthesis, but let me grab the specific. Actually, we are not doing multi-step. We are not doing a multi-step reaction. It's part of the multi-step. The multi-step is done over 3 weeks. Last week, it was oxidation, part of the experiment. Today is esterification experiment. Okay, Julia, that's also you're explaining about the multi-step reaction. We are only performing one of the many steps of the reaction today. production of methyl benzoate from benzoic acid and methanol through Fischer esterification of, okay, Fischer method of esterification. Very good. Yes, Olavia, yes, Michael, the Fischer esterification of benzoic acid. Okay, that is the reaction, and which is the purpose of the experiment also. So we are preparing methyl benzoate from benzoic acid. Okay, so Melissa, can you tell me what's the purpose of using sulfuric acid in this reaction? What's the purpose of using sulfuric acid? First of all, let me check your here. Yes. Melissa? Taylor? Your notes, okay, sure. Taylor, sulfuric acid is used as a catalyst for this reaction. And the reaction is esterification reaction. So one of the reasons why do we have to use catalyst in this reaction, and we are using sulfuric acid as a catalyst, and that is correct. When you look at this reaction, starting with the benzoic acid, which is a carboxylic acid to begin with, and you end up with ester, the reaction in general is called substitution reaction. A specific reaction is an esterification reaction, and more specific than that is called Fischer esterification, where your acid is a carboxylic acid. So esterification could come from nitric acid, sulfuric acid, and other acids, but when you have carboxylic acid, the methodology is called Fischer esterification. So the product is ester. In this nucleophilic substitution reaction, your nucleophile, what's your nucleophile? Cindy, can you tell me what's your nucleophile? Gian or Cindy, what is your nucleophile in this case? Okay, alcohol. Okay, very good. Very good. And there were a couple questions. I was also reading the questions in the chat area. The alcohol is the nucleophile. Alcohol and water, they are both nucleophile, but they are weak nucleophile. So when the nucleophile is weak, the reaction is going to be very slow. And the nucleus also, when you have your benzene ring attached to this carbonyl group, normally the carbon from the carbonyl group is the nucleus, or the center with the positive charge, which acts as a nucleus. So the nucleophile is supposed to come and attack this carbon. But since your nucleophile is weak, and also your nucleus is supported by the benzene ring. Benzene ring is a very good electron donor group, and it can support this nucleus. And it doesn't. So the carbonyl group from the benzoic acid is not very reactive either. So what you do, you bring in the H+ from sulfuric acid to protonate the carbonyl group, and when you protonate, it's going to bring in the positive charge. And when you have the positive charge on the carbon, then then you have basically like a carbocation formed here. So it makes your benzoic acid a lot more reactive to a protonated acid, which is a lot more reactive toward a nucleophile. The nucleophile would come in now and attack that carbon. So because the nucleophile is a weak nucleophile, you have to bring in a catalyst to use it. So it's not always a dehydrating agent. That was another comment in the chat area. In this case, is a catalyst that is going to come and basically protonates and makes the leaving group to leave easier, and the nucleophilic attack is going to take place. This mechanism is the mechanism that it is acceptable mechanism. They sometimes, there were another book, it explains that hydrogen H plus is going to protonate DOH, and then OH leaves as H2O. And this mechanism from the different sources, the protonation is going to happen in the carbonyl group, and this mechanism also is a supported mechanism. So this one is the one that we are using for the lab. We're just saying it's going to protonate the carbonyl group and make the nucleus more reactive. So you have all these steps are reversible steps. That means this reaction is going to reach equilibrium quickly, and if it reaches equilibrium, that means that percent yield is not going to be very high. In order to make the percent yield greater for this type of reaction, so again, in general, is a nucleophilic substitution reaction, specifically is Fischer acidification. Your reactant or limiting reactant is benzoic acid. Your reagent is alcohol, or the second reactant, or excess compound is alcohol. Sulfuric acid is the catalyst, and methyl benzoate is the product. This reaction, what you have here, this reaction is used for your calculation, and that's the reaction for today's experiment. The one that is explained on the first page, this one, the multi-step that you go from benzene to 3-nitro-methylbenzoate or meta-nitro-methylbenzoate. This multi-step, it's happening in different experiments. Last week we did this experiment that was oxidation of toluene, which gives the benzoic acid, and if you had chlorotoluene, it would give you chlorobenzoic acid. Today we are starting with the benzoic acid, and we are going to methyl benzoate, and next week we will do the nitration of an ester. So when we are dealing with this reaction, limiting reactant, benzoic acid, excess compound, alcohol. Why do we make the alcohol excess compound? When you look at mechanism for this reaction, you see that they are all reversible steps. So if it's reversible, that means it reaches equilibrium. And when it reaches equilibrium, Le Chatelier's principle applied to system at the equilibrium. In order to make the reaction goes forward and forms more product or increase the percent yield, you either have to increase the concentration of the reactant. That means you are putting the excess amount of methanol. The other way that you can make this reaction go forward is to remove H2O. You can remove the H2O by removing the water. You can remove the water by applying heat, because water boils at 100 degrees Celsius, so it can leave the reaction container, or add anhydrous agent, not like a calcium chloride powder, because that's too messy. Silica gel beads that they look like glass beads, you drop in there and they absorb water, they get like enlarged and absorbs the water, so it makes the reaction go forward based on Le Chatelier's principle. The product is methyl benzoate. As you see in that reaction, boiling point is provided. That means this compound is liquid at room temperature. So today you do not have melting point to measure because your product is liquid. But how would you know if the reactant has changed the product? Then you have to confirm it. And the way you confirm it is by taking IR of the product. The IR, I'm going to show you the IR spectrum, but first we are going to go through the procedure. So you will see that the IR spectrum for methyl benzoate looks different from the benzoic acid. Methyl benzoate, IR for methyl benzoate is provided in D12 in the same folder that you find the video for the experiment, and just right after the video. And for benzoic acid, you can search for IR spectrum for benzoic acid. So you can compare kind of apple to apple and see what is, how did the IR change going from benzoic acid to methyl benzoate. Okay, so we have excess amount of methanol in this case. You want to make sure that the reaction goes for completion. So you're adding 10 grams of benzoic acid and methanol, and then you are going to place in the ice bath. Therese, can you tell me why do we have to use ice bath? This is before step 2. First, you are going to place in the ice bath. Any idea why we would put the reaction mixture in the ice bath before we move to the next step, which is adding sulfuric acid?
I'm not sure, but I would say that I'm not really sure. I'm not sure. When I read that part, I wasn't sure why we place it in the ice bath. I want to say to prevent it from reacting or slowing down the reaction because we're using a catalyst in this reaction. I'm not sure.
Okay, how would it actually help? So you're on the right track. What you're thinking is, is on the right track, but I want to see if we can elaborate on that or be a little bit more specific about how it's going to help the reaction. Or what would happen if you don't put in the ice bath? What do you think will happen?
Possibly benzoic acid might turn into something else quicker, and I'm not sure.
Okay. When you are adding the strong, is a concentrated sulfuric acid. Okay, when you are adding concentrated sulfuric acid, if the reaction mixture is not cooled down to low temperature, is an exothermic reaction. So it can, let me look at the chat so make sure that I am not missing the answers. Sulfuric acid is very reactive and it can cause a lot of heat. Very good. And when it causes a lot of heat, it can cause boiling, foaming out of the container, and boiling of the methanol. And if it boils, it's going to bring particles of the acid out, and it can be dangerous. So you would see like film of acid coming out of the container. By cooling it down, you are going to lower the temperature. So when the heat is released, it's going to, of course, heat would be released, but it's going to go from let's say, from 5 degrees Celsius to 20 degree or 30 degree, but it's not going to boil off the reaction mixture. Is a safety factor, basically. So chilling the reaction mixture is a safety. Due to the safety, we want to lower the heat that is produced in that step. Very good. Denise, can you, next part you're doing reflux. What's the purpose of reflux in this reaction? So after we add the acid, then we reflux for 1 hour almost. So what's the purpose of using reflux in this reaction? Can you be a little bit more specific on that? Do we have to do reflux for temperature? For high temperature? The vapor of the solvent. Reflux is to return, right? Vapor of the solvent. So what's the purpose of reflux? You don't want to lose our solvent. Okay, very good. And is to prevent loss of the solvent or solution, whatever being tested, and the acid maintain high, let me see, I think the last one was maintain equal temperature for over heat methanol, since its boiling point is 65, to keep the temperature constant at the boiling point. Okay, I just want to make sure to spend some time on that because, you know, I could have just say why you're doing reflux and move on. And I'm just hoping that by you answering all these and giving this comment, so you would remember it. So next time, this is the second time you're doing reflux, and if you do the reflux a third time, it becomes like natural. When would you do reflux? Reflux is done whenever, in a chemical reaction, whenever high temperature is needed over long period of time. As I said last time, if you only need high temperature, you can boil the sample. If it's for 1 or 2 minutes, you just heat up the sample for 2 minutes. But if it takes time, if it takes long time for reaction to happen, you can just leave it on the side at the room temperature for a long time and wait for the reaction to happen. But based on the thermodynamic of this reaction is not a very fast reaction. For obvious reason, your nucleophile is not a strong nucleophile, and the nucleus that you have is not very reactive, positive center either. So it does need help. It does need high temperature and for a long period of time. Whenever you need high temperature for a long duration of the experiment or duration of the heat, you have to run under the reaction under reflux, so you don't lose the vapor. Okay, you don't lose the vapor of the solvent does not dry out, and you also provide temperature, high temperature near boiling point of the solvent for a long period of time. So just in short, reflux is used whenever you need high temperature for a long period of time. So if that is the condition for reaction, you need to use reflux. Very good. So you don't want to lose the solvent either. So you want to make sure the solvent is maintained. Okay, so after the reflux, then you are going to cool it down and transfer to a separatory funnel that contains 50 milliliters of water. And question for who has that? Karina, have you answered any question? Okay, Karina, can you tell me what's the purpose of using separatory funnel in this case, in this experiment? Why are you using separatory funnel? Separator funnel is used for do you remember from 1040? I'm sorry, from organic 1, what is the use of separator funnel? In which experiment did you use separator funnel? In extraction, right? So separator funnel is used for extraction, and when you are doing extraction, that's a purification method. So why do we have to do purification in this case? Because as you see in this reaction, you could have excess of leftover of methanol, you could have leftover of sulfuric acid, you could have water, you could have benzoic acid. All of these could be leftover. And the only product that you want is the methyl benzoate. You don't need anything else. You only need this one. So you have to purify your sample. So what is the extracting solvent in this case? If Jones, have you answered any question? Jones, what's the extracting solvent used in this experiment? Can you use ethanol as extracting solvent? Can you use ethanol for extracting solvent or as extracting solvent? or what extracting solvent is used in this? T-butyl methyl ether is used. Okay, T-butyl methyl is used. And can you use alcohol as extracting solvent, like methanol or ethanol specifically? Anyone? Why not? No, we cannot use it. The reason for that is we cannot use it because when you use the water in the separator funnel, so when you have the mixture in the separator funnel, that if you remember correctly from the organic one, it should stay in two separate layers. So whatever you are using as extracting solvent, it should be immiscible in water. Ethanol dissolves in water and it forms one layer. Methanol, same thing. That's why in this case you are using ether, or you could use methylene chloride, something that does not dissolve in water. Okay, should not dissolve in water because you want to, based on the density, they should form two separate layers, like oil and vinegar type. So you cannot use ethanol or methanol as extracting solvent, and you are using ether. After when you add the ether from this reaction, methyl benzoate goes to the ether layer. If there is any leftover of benzoic acid, could go to ether layer, but water, acid, sulfuric acid, and methanol would dissolve in aqueous layer. You drain the aqueous layer. That's like how you separate the methanol and you separate the sulfuric acid and water. On the next step, you are going to wash it with sodium bicarbonate. And can you tell me why you are washing this with sodium bicarbonate? Saturated sodium bicarbonate. What's the purpose? Victor, have you answered the question? Brianna? Victor or Brianna, can you tell me what's the purpose of using
I thought it was for a purpose, but yeah, to remove unreacted benzoic acid.
You are using, let me, the chat also, a few answers came in. Yes, that is correct. Yes, you are going to remove the benzoic acid, because benzoic acid, it would come into the ether layer because it doesn't dissolve in water. So you have to somehow remove the benzoic acid. Ideally, there should be no benzoic acid, but it's a reaction. And if there is any leftover of benzoic acid, then you have to remove it. To remove, when you are adding sodium bicarbonate, it would react with the acid. It's an acid-base reaction. You would get sodium benzoate, which dissolves in water, just like experiment 12. Too much thinking, but experiment 12, before you add the HCl, you had sodium benzoate. It dissolves in water. And then the other part gives the hydrogen carbonate, and hydrogen carbonate would break down to H2O and CO2, but it dissolves in water and it will be separated. So the aim is to purify methyl benzoate from water, from alcohol, from benzoic acid. So sodium bicarbonate is used to remove that. On the next step, you are using saturated sodium chloride. Brianna, have you answered any questions? If not, answer this one, please. What's the purpose of using saturated sodium chloride to wash the organic layer or the ether layer? Brianna? I don't have the attendance up. Are you here? Okay. Yes, to separate the organic and the aqueous layer. okay, what actually does, like when you eat like too much salt or salty food, you get thirsty. So it's the same concept. When you pass the saturated sodium chloride solution through organic layer, it absorbs all the water. It's kind of dehydrating agent, but in the liquid form. So it takes away most of the water out of the organic layer. So it's basically to absorb or to remove water from organic layer. And next step, you're adding, after you separate, you add calcium chloride. What's the purpose of using calcium chloride? Did you all answer at least one question? Dry the solution by removing traces of moisture. Very good. Drying the solution. So if there is any leftover of water in the organic layer, when you add the calcium chloride, it's going to remove it all. Okay, very good. Then you are going to heat up the sample. When you heat up the sample, you remove the ether. What is left is going to be ester or methyl benzoate. Methyl benzoate is ester. It has like all esters, they have like fruity flavor, and they are used to food as an additive to give taste, like cherry flavors, like a cherry flavor, strawberry flavor, or like for chewing gums. You see there, if there are different flavors, basically what's added there is the ester that it gives those flavors. As far as the experiment lab report goes, you need the data. You don't have the melting point, but you do have the mass. With the mass, it comes the percent yield for the experiment. So percent yield, and then the IR values. Let me show you what I mean by the IR values. The IR spectrum that we have here, going to share the D12. If you go to, to experiments and lab work, go to experiment 13. After the video link, there's IR spectrum. The IR spectrum looks like this diagram here. This is for the methyl benzoate or for ester. If you notice here, the location of the peak is at 1718 or 1717.8. This peak here is specific for esters. Carboxylic acid, they have very similar, like benzoic acid has a very similar strong peak, but appears at like 1680 or between 1680 and 1700. The shift from 1680 or 1700 to 1718, that indicates that this is not benzoic acid, it's not coming from benzoic acid, it's coming from methyl benzoate. If you had methyl benzoate has a OH group, because it's benzoic acid, has a OH group, then you would have a peak, like a broad peak going from 2500 to 3500, very broad round peak. Now is not there. And it's good that it's not there, because if it was there, that means you had OH. And the other reason, your product must be completely dry, so you use sodium chloride saturated to dry the organic layer. Then you add calcium chloride to remove any trace of water, because even if you have complete reaction and there is no benzoic acid left, if you had water as impurity, it would show a peak around 3300, broad peak for OH. Then you didn't know that OH is coming from water or is coming from leftover of benzoic acid. So what I suggest you to do, you may want to write down, because from now until you write your lab report, it might, be a couple hours or a couple days. What I suggest you to do, search for IR spectrum for benzoic acid and compare to the IR spectrum for methyl benzoate, which is the product that you have in D12, and see what are the changes. Specifically, the OH peak should disappear because benzoic acid has OH, methyl benzoate doesn't. And the other change would be the peak around 1700 for benzoic acid would be at 1700, but for methyl benzoate or for ester is moving up to 17, 18 almost. And this change indicates that your product is ester. And just like melting point, that if it's close to the known value, it assures that yes, your product has formed and is pure. In this case also, IR spectrum is used to determine if the product has formed and if the product is pure. As I said, if you had a peak here, like at 3300, very broad peak, not these sharp short peaks, is like very broad peak. That means you had leftover of either benzoic acid or water, and both of them would have count as impurities, so your sample was not pure. But this spectrum, it indicates that it's methyl benzoate and it is pure sample. The values from IR, it should appear at the same time with the percent yield. Percent yield and IR values should appear in abstract. It should appear in conclusion, and also for data result and also discussion, because that's you're defending in the discussion part that yes, the product has formed. Okay, do you have any questions for me?
Dr. Mamari, I just have a question about, you said something about the OH peak would disappear in which one?
Okay, if you compare the, let me go back to, actually I'm going to stop this and I'm going to go back to the lab manual so I could show you the reaction one more time. And from this reaction that is highlighted, you see benzoic acid has a OH, right? Methyl benzoate doesn't have OH, so the reactant has OH, product doesn't have it. The broad peak for OH, it should disappear because that means that now you have the product and not the reactant. If there was leftover of reactant in the product as form of an impurity, then you would have seen a peak around 3300 or between 25 to 3500 for OH. So to answer your question, that peak was for OH. And since your product doesn't have OH, the peak for OH should disappear, should not be there.
Thank you.
You're welcome. Okay, any other questions you might have? No questions? Okay. Going to stop the recording, call for attendance.